Actually, we could all introduce one.
That's right. Okay. So welcome. I'm just going to turn it over first to Chris McGee, who's here from ESD, the Engineering Systems Division of MIT.
Right, and we're co-sponsors along with NECSI of this series of seminars. I think it's the first one this fall.
It is. That's correct.
So there'll be more. But I took advantage today, and I've already introduced our guest today, because I took advantage of him coming here for this to get him to participate in the class that I could teach. And we had a lot of fun with Professor Kauffman this morning already.
So I'm Yanir Bar-Yam, and I'm the president of the New England Complex Systems Institute. And if you haven't yet been to our seminar series, a special welcome, and for everybody else, welcome to the new year of our seminar series. The purpose and framework of these seminars is the joint recognition by the Engineering Systems Division and the New England Complex Systems Institute that science and technology today have new opportunities to contribute to solving the real world problems that we're facing, of which there are plenty. And in that context, we have decided to jointly sponsor this series to bring people who really can help us understand many different aspects of what's going on in the real world, and also the fundamental science and engineering developments that are making that possible. So again, welcome. Now, today we are very, very happy to have Stuart Kauffman here with us. We are going to be talking about a radical change of our scientific perspective, really what it means to think about science as a way of understanding the world, and Stu will be talking about that. But before he does, I want to say a few words about Stu. Stu is a very good friend for many years, but Stu has been tweaking and saying radical things about science and our understanding of the world for many years, and to the dismay of many people in the traditional approaches, he's been incredibly successful at doing so. I think that's pretty fair to say.
I'm still alive.
That's right. And so it's he has many, many specific contributions, but the general tenor of his contributions is really to challenge fundamental assumptions, fundamental ideas, and show that there are really new ways to think about the world around us. And that's a very powerful thing to be able to do. Stu is the recipient of a MacArthur Award, but he's also the recipient of our highest award of the complex systems community, the Herbert A. Simon Award. He received that, was given to him about 10 years ago at the International Conference on Complex Systems. And I don't remember exactly the year, but
2000,
2000. Fabulous. So without too much more, I think that we're very happy to have Stu with us. As I said, our time is limited. I'm sure that we have experience that conversations with Stu tend to go on for a long time. So we will let him have his primary say, and we'll have a conversation, but the conversation will end at 2. People who would like to extend the conversation, Stu is great about staying in touch, and we will have other opportunities to talk with him. Stu.
Well, I'm very, very pleased to be here. And Chris, thank you. I enjoyed being with your class today. And Yanir, old friend, thank you for inviting me. I don't have a clock, so I need somebody to tell me as time goes by a little bit, unless somebody has a watch that I can borrow, something like that. Okay. So forgive me for sitting down. I have a sprained ankle that I just re-sprained, and I have to sit down. I'm going to read my talk. You've all got it. I'm going to read it because it's 31 points, and it's in the process of being written up. Giuseppe Longo and I are collaborating. Let me tell you about Giuseppe. He's a senior mathematician, a few years younger than me, in Paris, just moving from the École Normale Supérieure to the École Polytechnique in Paris. and we just spent a delightful 5 days together. I'm teaching at Burlington this fall at the University of Vermont. And I don't think Giuseppe knows that he's down as an author on this, but we are writing a paper together that he's writing this week about this, and I know that he's happy with the ideas in this. So I don't really have his permission for him to be here, but I certainly want to acknowledge him. He's just wonderful. I really do want to talk about something that may be very large, but I also may be very wrong. Max Aldana, who's an old friend in the audience, has already emailed me telling me that I'm fundamentally wrong. So we're going to have, actually he didn't say fundamentally wrong, so might be wrong. But maybe we can talk about Max's point if we have time. So I apologize for reading, but it can work pretty well. 2,500 years ago, Heraclitus said, "The world bubbles forth. There is in this fragment of thought an image of the world becoming beyond entailing law." Somewhat similarly, in Genesis, God creates all beyond entailing law, setting Adam in dominion over all of creation. With Newton and his differential and integral calculus, 3 laws of motion, universal gravitation, and initial and boundary conditions, integration of the differential equations form of the laws of motion, say for billiard balls on a table, of known boundaries, yields by deduction, that is to say integration is deduction, therefore by entailment, the entire future and past trajectories of the balls. Newton taught us how to think. It's stunning. One mind did it all. We're still doing what Newton told us to do. All these years later, I mean, we've got Einstein and we've got quantum mechanics, but then you're talking about the dynamics and the trajectory of a probability distribution. So it's still the same conceptual framework. With Laplace, this became the trajectory of all the particles in the universe, hence by entailment, the entire future and past of the universe. This is the foundation of reductionism with us today. Now this has societal implications. They're huge, and I'm as concerned with them as anything else, and that's why I'm particularly excited to be. This is one of the bastions in the United States of scientific and engineering thought. So I am bringing my first presentation of this into dangerous ground. Don't kill me. Early sociologist Max Weber said that with Newton we became disenchanted and entered modernity. Pause and think for just a second about it. A century earlier we had the white and the black magi. Black magi thought that if you had the magic incantations, you could stand nature on her head and make nature do your bidding, to wrest power over nature, God's promise to Adam in warped form. With Newton, we enter a mechanical universe. It's Descartes' res extensia come to fruition. So no longer does magic work. The theistic God becomes a deistic God with the Scottish Enlightenment, or the God of the gaps in modern society, or in the last 350 years. And we entered modernity. Well, we do. We get the Enlightenment, which is what? It's down with the clerics, those obscurantist religious fools, up with science. Why? For the mastery of nature, for the ever betterment of mankind. Right? That's the driving force of the Enlightenment. We get the Industrial Revolution, and we're into modernity. I've already told you about Giuseppe Longo. I'm going to argue for, by the way, I'm 72. That matters because I think at age 72, Brian, I'll ask later how old you are, but
I'm 71.
Yeah, you're not as old as me. When do you get to have a really presumptuous title? And if I can't have a presumptuous title at 72, my mind's going to stop working in 2 or 3 years. So I've got a narrow window for presumptuous titles. So here it is, The End of a Physics Worldview, Heraclitus and the Watershed of Life. we will find ourselves, this is amazingly presumptuous, but I think true, beyond Newton, Einstein, Schrödinger, even Darwin, even amazing Darwin, beyond entailing law in the becoming of life. We may become re-enchanted, and we may find a way beyond modernity, which is the biggest civilizational issue. I think in a way we can't articulate, we're lost in modernity. And I think there's an unrest around as we sense this but don't know what to do. So, my points are numbered and I'll say the numbers. Of course you can follow them, but 2. So I start the scientific part. Evolution is neither sufficiently described by quantum mechanics nor by classical physics. So this is really striking. We all know it, but I didn't say it to myself until around 4 months ago. Mutations can be quantum events on the Copenhagen interpretation. They are random, indeterminate, and acausal. An example is quantum tunneling, which can facilitate the conversion of the keto-enol tautorism of the bases G and T due to tunneling of one proton in the OH group. The wrong tautomer leads to false base pairing, so you get a point mutation, and it's been shown by experiments. So it's really true that quantum events can cause mutations, and they're quantum random, and indeterminate, and acausal. But evolution is not random, and you all know it. For example, the octopus has a camera eye that's evolved independently of the vertebrate camera eye. They're nearly identical, except they do it right. They have the blood vessels behind the retina, and we stupidly have them in front. I know I'm a doctor. You can see the blood vessels when you look into the eye. Well, we'll see a little bit later that defining random is harder than you think, but I think we would all agree that that just doesn't look random. So if you agree with that, and by the way, the same kind of convergent evolution is seen in the marsupials and in the mammals, like in the marsupial wolf and the mammalian wolf. That means that evolution is neither determinate nor random. It's something new. It's some kind of superposition of quantum and classical, whatever we're going to mean by classical physics, whether it's a large number of degrees of freedom, therefore a highly probable thing that could go awry, or whether it's quartz classical. So we have to think about life anew, point 1. Point 2, I have to tell you about Darwinian adaptations. You all know, but suppose I asked Darwin, Charles, we're on first name basis. Actually, it's Chuck. Okay? Chuck, what's the function of Kauffman's heart? He would say, it's to pump blood. But I'm a doc, and I look at him and I say, but listen, my heart makes heart sounds. And it jiggles water in my pericardial sac. Why aren't those the functions of my heart? Darwin would say, the function of your heart is to pump blood because it was selectively advantageous in your ancestors to have a heart that pumped blood. That's why you have a heart. And that's why the function of your heart is to pump blood, not make heart sounds and jiggle water in your pericardial sac. There are 2 big points here. 3. First, Darwin's offering a selectionist account, and I think we'll all buy it. Point 1. Point 2, the function of the heart, it's 4 points. The function of the heart is a subset of its causal consequences. It's pumping blood, not jiggling water in my pericardial sac. Point 3 is the word function in this sense doesn't exist in physics. Okay, balls rolling down hills don't have functions. And point 4 is Darwin's actually telling us why hearts exist in the universe. And I want now to tell you why that's a problem. So I'm on to point 4. And it's easy to make and very interesting to think about. There's something physical going on. We've made all possible atoms that I know of in the universe. Now you all know that a protein is made of 20 kinds of amino acids. A typical protein is length 200 or 300 amino acids. How many possible proteins are there length 200? they're going to be a lot longer than that, but let's just take 200. Well, it's 20 times 20 times 20 times 20, 200 times, which is 20 to the 200th power, which is 10 to the 260th power. Now, as you all know, there are 10 to the 80th or so particles in the universe. The shortest time scale is the Planck time scale of 10 to the minus 43rd seconds. If you work it out that all of the particles, ignoring space-like separation, are busy on the Planck time scale doing nothing but making proteins length 200, it would take 10 to the 39th power times the age of the universe to make all possible proteins once. That means something physical. It means that the universe at levels of complexity above atoms is on a unique trajectory. We will not make all possible complex molecules. We won't make all complex organs. We won't make all complex organisms. I'm being a biologist, okay? And being a musician, we won't make all possible operas. Right? That means that history enters when what's possible is vastly larger than what can actually happen. So the universe is grotesquely non-ergodic. And when Darwin says you have a heart because of selective advantage in your ancestors, he's explaining why a complex thing like a heart exists in the universe. That's big. Getting to exist is a big deal. Point 5. We're going to get to something that you don't know about. Darwin said, you know what, a causal consequence of an organ of no selective use whatsoever in a given environment, like jiggling water in my pericardial sac, might turn out to be useful selectively in a different environment, so be selected. They're called Darwinian preadaptations, not meaning that evolution has foresight, just that it turned out that way. And Steve Gould invented the word exaptation to cover that idea, so it means the same thing. I'm only going to give you one example of a Darwinian preadaptation. They're all over the place in biology. This one happens to be my favorite for no good reason. Some fish have a sac called a swim bladder. It's partially filled with air, partially filled with water. The ratio of air to water adjusts neutral buoyancy in the water column. Now, paleontologists believe that swim bladders evolved from the lungs of lungfish that were flopping from puddle to puddle. The water got into some lung, and it was, quotes, poised to become a swim bladder. Let's suppose the paleontologists are right. So I have 3 questions. First, did a new function come to exist in the biosphere? Sure, neutral buoyancy in the water column. Tell me if at any point you disagree. Agree? Second, did it change the evolution of the biosphere? Sure. And so I always say 3 things. New fish species with swim bladders, new proteins evolved, and I said, but we'll come back to it because I realized something amazing about this. The swim bladder, once it exists, is a new niche. It's a new, what I will call, adjacent possible empty niche, because a worm or a bacterium might evolve to live in the swim bladder. Agreed? So a new niche came into existence. Okay. Now I'm going to come to my hard question. I love this question. Just for human beings, do you think you could name all possible Darwinian preadaptations in the next 3 million years? Anybody think so? I mean, I know what you think because I've asked about 10,000 people now. This is a neat moment in your life. Feel your mind going blank? Imagine trying to do this. Now I'm going to give you a first pass, and then I have finally figured out a better way to say it, and I'll tell it to you later. Here's why it's hard. How would you list all possible selective conditions? How would you know you listed them all? How would you name all possible bumps and wiggles on one or many organisms that might turn out to be a pre-adaptation? It feels impossible, and I'll show you later why it's impossible, but that's a first pass at it. Now, I need to define a notion that I call the adjacent possible. So let me do it with a liter of 1,000 kinds of organic molecules. Call that the actual, very technical term. Now think of all possible one-step reactions. Let them happen. You might get some new kinds of molecules. Call the new kinds of molecules the adjacent possible. So I've just defined it. It's perfectly well defined for a liter of 1,000 kinds of organic molecules and an enthusiastic organic chemist. Now I'm going to point to the adjacent possible of the biosphere. See if you agree. Once there are lungfish, swim bladders are in the adjacent possible of the evolution of the biosphere. We agree? 2 billion years earlier, before there were any multicelled organisms, swim bladders aren't in the adjacent possible of the evolution of the biosphere. Do we agree? You've just submitted to something that's going to surprise you. We do not know the adjacent possible of the biosphere into which the biosphere is going to evolve. I'm going to say it again. We do not know, because you said we can't list all possible Darwinian preadaptations, we do not know the adjacent possible of the biosphere into which it's going to evolve. We really don't know. Now that means something terribly important. Let's ask if we can make probability statements about the evolution of the biosphere. So let's start by flipping a coin. All this is really weird, okay? So suppose I flip a coin 10,000 times, and I want to calculate the probability that it comes up heads 5,422 times. I didn't go to MIT, but I know how to do it. You have this thing called the binomial theorem, okay? And even if you can't calculate it, you can look it up in some table as a Gaussian approximation, and you got it, right? But notice that you knew ahead of time all the possibilities, all heads, all tails, all 2 to the 10,000 possibilities, agreed? You knew the sample space of the process, and therefore you could construct a probability measure. But we don't know the sample space of the process of the evolution of the biosphere by Darwinian preadaptations. Therefore, there's no known means that we have now to construct a probability measure. We don't know the space we're talking about. So we cannot construct a probability measure. Now, I'm going to wind up skipping a point later, but this applies to the evolution of the economy, the econosphere, and human life and cultural life. I think it applies to the evolution of life. And it means something personal. It means not only do we not know what will happen, which is the case in flipping the coins, we just got to wait and let chance do its thing, mainly deterministic chaos. We don't even know what can happen. But if we don't know what can happen, we cannot reason about it. That means reason is an insufficient guide for living our lives. When I first realized this, I thought, my God, what am I supposed to do? Then I thought, we've been doing it for 3.7 billion years. We've got to be able to do it. And we do it. It becomes a deep question, how? Well, we at least use reason, emotion, intuition, and sensation, Jung's 4 types, and metaphor, and poetry, and jingle bells, and whatever. Somehow we do it. But it's fundamental. We don't know what can happen, yet we have to live our lives anyway. Okay, now, side comment. Shannon, in 1948, in this very institution, invented information theory. This revolutionized a lot of technology. I want to now tell you that Shannon's information theory is utterly useless for the evolution of the biosphere, and I can prove it to you very simply. Shannon computes the entropy of the source. Remember, he's got a set of symbols Okay, he's considering binary strings length n. There are only 2 to the n possible binary strings length n. Suppose he specified n. And then he does pi log pi and sums it up, takes minus the sum, and that's the entropy of the source. You got to know the sample space, right? If you don't know the sample space, you can't compute the entropy, so you can't compute Shannon information. So Shannon's information doesn't help us with the evolution of the biosphere. It's also nutty because what's the source? But that's a different issue. The same problem infests Kolmogorov. Kolmogorov says, what's the sort of computer program that will give you a specific symbol string out of an ensemble of symbol strings where you know ahead of time the set of the possible? But we don't know that. So Kolmogorov information doesn't work here either. Something mysterious is going on that we're not used to. I'll tell you what it is later, but in preamble, the phase space keeps changing in ways that we can't pre-state. And Giuseppe Longo, God bless him, I said appealing to a God that I don't believe in, but kind of wished I did, gave this amazing talk in AICS saying, in physics you can pre-state the state space, but in biology you can't pre-state it and you don't know it. And I thought, my God, that's exactly what I've been trying to say with my adjacent possible, and that's why we're writing a paper together. Now I'm going to tell you something that stunned me. My wife Elizabeth is sitting over here. We have a patio in our house in Santa Fe, and about 4 months ago, I looked at her and I said, my God. And she said, what? And I said, I just realized something. I mean, you know how husbands and wives are. And she hit me over the head with a frying pan. And after I woke up, I remembered it. So let me ask you a question. Do you agree that the swim bladder, once it exists, is a new adjacent possible empty niche? Because some worm or some bacterium might evolve to live in it. Fair enough? Mm-hmm. Okay. So it's a new possible direction of evolution, right? Now, do we think selection acted on a population of fish to make a Jim Dandy swim bladder? Sure, probably, okay? That's not my question. My question is the next one. Did selection act to create a new possible empty niche? No. Pause. Did selection act to create the swim bladder as a new empty niche in which a worm or a bacterium might live? Pause to take it in. The answer is no. Do you agree? It worked to make a working swim bladder. It didn't work to make a new niche. Now, what does that mean? That means that without any selection at all, the biosphere is building, creating, the very possibilities that it will become. Isn't that amazing? The biosphere is building the very possibilities that it will become. Now, as a matter of fact, here at MIT, I'll tell you, technology is doing the same thing. And just very quickly, I'm not going to read that point, but to get from the invention of the Turing machine to the ENIAC, to the mainframe computer, to the personal computer, to word processing, to sharing files, to the World Wide Web, to selling things on the web, to content on the web, to browsers like Google, to Facebook, is a bunch of niche creation and seizing of niches. The biosphere, the econosphere, is building willy-nilly, with nobody's intent, its own future possibilities of becoming. And one more point going back to, this is a fundamental point, the swim bladder. Where, you see, we don't have to worry about conscious intention when we're thinking about the biosphere, and we do have to worry about conscious intention, whatever we think about consciousness, when we're talking about the economy. So we've got the swim bladder, and here comes a worm, and it's going to evolve to live in the swim bladder. And what happens? Some quantum indeterminate acausal mutation happens, and you get a slightly improved capacity to live in the swim bladder, and you're on your way to evolving a worm that can live in the swim bladder, right? But it's acausal. So the new niche does not cause the worm to be able to live in it. It enables the worm to be able to live in it. And I'm falling in love with the word enable. It means to make possible. That's literally what's happening. And the same thing is true in the economy when the widespread sale of the personal computer creates a market niche that enables the invention and wide sale of word processing. It enables, it doesn't cause. I want you to take this in, and I want to call this radical emergence. We all throw around the word emergence. Roughly what we mean by emergence in our now enlightened early 21st century talk is something like this. I've got a complex system with lots of degrees of freedom, and they're all hooked up to one another, and they're all banging around. And if I look at the collective degrees of freedom, they do something I never would have expected. For example, I invented random Boolean nuts when I was a kid. And it turns out they have an ordered regime and a chaotic regime, and they go through a phase transition where they're critical. And a bunch of us discovered that. And it turns out that cells may very well be critical for lots of interesting reasons, and we're measuring that. Well, criticality is an example of quotes an emergent property. It then becomes a question afterwards whether you could have deduced it. So we all know that in Phil Anderson's More is Different, where Phil talks about getting new laws at ever higher levels, it remains a question about whether or not you could have deduced it after the fact from the underlying laws. And there's debates in all directions. Radical emergence is different. Okay? Radical emergence of the worm living in the swim bladder, I'm going to get to this in a minute, I'm going to claim we can't deduce it from anything. So there's radical emergence happening in the world. So I've now talked about enablement. So point 13 is the one about the economy. I'm going to skip it. So this leads in 14 to a profound new issue. Is the becoming of life and our lives entailed by some law in the Newtonian sense, the reductionist view? I'm going to, with Giuseppe Longo, argue that the answer is no. No law, in the sense of differential equations, initial and boundary conditions, will yield the evolution of the biosphere or the econosphere or human life. I come back to Max Weber's statement, with Newton we become disenchanted and entered modernity. So once again, I've just point 16 you already know. Newton's laws of motions, ordinary and partial differential equations, initial and boundary, integrations, deduction, and entailment, all that. And then I'm repeating again that evolution is not sufficiently described by quantum mechanics or classical physics. I want to move to something that I think is essential for this discussion, and it depends upon the great philosopher Immanuel Kant. Kant said, and roughly, an organized being is one in which the parts exist for and by means of the whole, and the whole exists for and by means of the parts. This is only 240 years ago or something. He was an amazing mind, just stunning. Okay? Now I'm going to give you an example of a Kantian whole. Gonan Ashkenazi in the Ben Gurion University in Beersheba in Israel has everybody knows what proteins are. A peptide is a small protein. Gonan has a 9-peptide, collectively autocatalytic set of proteins reproducing itself in his lab. Roughly, here's how it works. Each protein speeds up or catalyzes a reaction that takes 2 fragments of one of the other proteins and binds them together in a proper peptide bond to create a second copy of the other protein. Okay? Such that each of the reactions that has to get catalyzed gets catalyzed by one of the other guys in the 9-peptide set. Now, if you call catalysis a catalytic task, This is terribly important to me. The set as a whole achieves catalytic closure. No peptide catalyzes its own formation. The set collectively catalyzes its own formation. Everybody got it? It's not a joke. Gonen's got it. And I'm going to see him in 5 days. In fact, a group of us are working with CERN trying to make protocells in the next 15 years. And the origin of I've been interested in the origin of life since, I guess I was about 30. Okay, this is the simplest example that I can think of a Kantian whole. Why? Well, first of all, notice that Gonen's set is a complex system that gets to exist in the universe as a complex thing, like a heart, right? It gets to exist. Second, it's really true that the whole coordinates the behavior of the parts, and the parts exist formed by means of the whole, and the whole exists formed by means of the parts. I didn't say that very well. The whole exists formed by means of the parts, and the parts exist formed by means of the whole. Notice that we can define the function of a peptide by the catalytic role that it plays in catalyzing some other peptide and sustaining the whole. So the word function makes sense, just as Darwin would like. So with Kantian wholes, all of a sudden, the word function makes sense. And it means something physical. It gets to exist in the universe. Now, you could still do a reductionist analysis on it after the fact, which wouldn't change my point. But if it's a quantum system, you've got to treat it as a whole. You can't treat it as a bunch of parts, which is sort of a side issue. I just want you to see that it's a Kantian whole. Next step. Take a skin cell in you that's dividing. It's achieving closure in some set of tasks as well. But it's a lot more than catalysis, and this is really going to be important to me, because it includes when the cell divides chromosomes separating in mitosis, it includes making membranes, it includes making chemosmotic pumps, it includes making microtubules that are doing all sorts of cool things, yes? That are all part of a set of tasks that achieve a closure as the cell divides. Fair enough? Notice again that the function of a part is a subset of its causal consequences. Okay? Now, I'm going to take what looks like a really funny step, but it turns out to be essential for what we're talking about. Can anybody in the room tell me all possible uses of a screwdriver? How did I get to screwdrivers? Well, I'm talking, so I get to. Tell me all possible uses of a screwdriver. Well, you can open a paint can. You can screw in a screw. You can use it to jam open the door. You can use it to jam close the door. You can use it to scrape putty off a window. You can use it to stab an assailant. You can tie it to a bamboo pole and spear a fish. You can rent the spear to the natives and take 5% of the catch. I'll tell you my favorite use of the following three objects. A screwdriver, a 4x4 foot piece of plywood, and a wall. Liz is a painter. I take the wall, I take the screwdriver, I orient the rigid, narrow edge at right angles to the wall. I prop up the plywood on top of the screwdriver, and I put Liz's wet painting underneath so that the rain won't fall on it. That's a perfectly fine use of a screwdriver. In fact, it's an elegant use of a screwdriver. Notice that the use of the screwdriver is a subset of its causal properties. For example, how wind whistles around the screwdriver on a windy day, right? What's our problem? The problem is, and this is profound, the set of uses of a screwdriver alone or with a bunch of other things is certainly indefinite. It's unbounded in some sense. Do you agree? Furthermore, there's no ordering relationship. There's not a first use and a second use and a third use and a fourth use, like the integers. Do we agree? That means there's no effective procedure to list all the uses of a screwdriver. There's no algorithm to list all the uses of a screwdriver. You can't do it. And that's why your mind went blank 20 minutes ago. You can't do it. The set of uses is indefinable. Now let's turn this to cells.
You're not describing a screwdriver, you're describing a long projectile object. A screwdriver is a subset of that. All the functions that you gave were not unique to a screwdriver.
Of course not. So a way of saying what you're saying is the following. For any object, there are multiple uses, or for any set of objects, there's multiple uses. And there may be multiple objects that can carry out the same use. That's your point.
So a screwdriver drives screws.
Sure, among other things. Right.
Well, that's the only thing it does.
No. Come on, I just held up Liz's thing holding up the paintings. Right?
But that's not a screwdriver, that's a long projectile object of which a screwdriver is a subset.
I scraped out some rotten wood from under my deck board with a screwdriver yesterday.
Thank you. My point, so let me say this again and go on for time, but we can come back and argue it later. I see what you're saying, but what you're trying to say is that if you could narrowly enough define a screwdriver, the only thing you could do is screw in screws. But if you give me a physical object, which happens to have the name attached to it called screwdrivers, he can scrape putty off the bottom of his drawer. So for any physical object or process, there are multiple, alone or together with other things, there's multiple uses that are indefinite in number and we can't order. And meanwhile, for any given use, there's multiple objects that can do it. I mean, you can get to the store by, jumping out of a helicopter and crashing through and grabbing some Cracker Jacks and rocketing out without ever paying. I just made that up.
He's taking your content, Wittgensteining you.
I've never been Wittgensteined. Let's come back to it. But I'm talking about the physical object that we call a screwdriver and pointing out that it can be used for multiple purposes. And in fact, that it's indefinite in number and that they're not orderable.
How do you know they are not ordered? I mean, I don't know a way to order them, but how do you know it's impossible to order?
I guess I don't know. Let me go on and assert that they're unorderable, and you tell me later how to order them. I haven't the faintest idea how to order.
Neither do I, but there might be.
What?
Neither do I, but there may be one day.
Let's come back to that, okay? Fair enough, because this is essential. What I just said is essential to my argument, okay? Because, so let me get away with it and then come back and maybe you're right.
I don't know that orderability is essential to the rest of your arguments either.
What?
I don't know that orderability is essential to the rest of your arguments.
Oh, cool. I'm glad I'm in a room that's willing to help a mere biologist. Let me go ahead. Okay. Now suppose that these are bits and pieces of molecules in a cell. Okay? What happens? Suppose, so here's the phrase that I find happy. I must be somewhere on this thing. Cellular screwdrivers and other processes and parts, like molecules in a cell, or pumps, or something else, alone or together, I think this is the right phrase, may find a use in an unprestatable Darwinian preadaptation, which is heritable and enhances the fitness of, say, a cell, so is selected by natural selection, operating at the level of the Kantian whole. It selects the cell. The cell gets to live, right? With this new funny use of some things in it that are a Darwinian preadaptation. And so it's grafted into evolution. A concrete example is the flagellar motor that you all know of in bacteria that allow bacteria to swim up glucose gradients. Well, in the great trial in Dover about with the with the intelligent design people, some microbiologists pointed out that the flagellar motor was a Darwinian preadaptation of a bunch of small proteins that were serving entirely different functions in other bacteria that came together to make the flagellar motor. Let's assume that they're right. It makes my point. Okay. It also devastated the argument for intelligent design. So, point 23. This is the terribly important next point. This selection at the level of Kantian wholes identifies the unprestatable but newly relevant variables in the evolving cell or organism. It's selection itself that picks out what's relevant. The pumping of my heart, not the wiggling water in my pericardial sac, and the being a flagellar motor. That's what's relevant. But we couldn't say it ahead of time. We couldn't say it ahead of time. But it came to exist in the non-ergodic universe. So newly relevant variables keep happening. So this is where I finally tie in with Giuseppe Longo, who's just wonderful, saying there's an ever-changing phase space in biological evolution, and we cannot prestate it. Just stop here. We're all trained scientists. All of our science imagines that we know ahead of time what the state space is. And then we have dynamics and nonlinear dynamics and attractors and bifurcations and stochastic processes and all the stuff that we all know, that it assumes that you know what the phase space is. Now, Max Aldana, who's an old friend, is sitting in this room, and he emailed me this morning, and he said, but wait a minute, physicists have been dealing with state spaces where the state space can change. And maybe Max can talk about this later. He was talking about a system in statistical mechanics where you go from having n particles to n plus 1 particles. I don't know that example. Let me give you an example of an extensible state space. I've got the game of life on a two-dimensional lattice. The fastest moving things are gliders, shot from glider guns. I'm going to put it on a finite lattice and start with a little pattern in the center. And I'm going to make my lattice get bigger and bigger and bigger and bigger and bigger, faster than the fastest glider, okay? So I'm always outside of the glider range. So I've got an expanding state space. But if Giuseppe were here, he could say this in math talk. I can't. I know ahead of time how to describe in a few simple words how to expand my state space. I know the relevant degrees of freedom, here, little spatial cubes, little spatial squares, I'm up one dimension, little spatial squares that I'm adding on to my state space. I know the relevant features of how the state space is expanding. And I imagine it's something like that, Max, in your case, but we can talk about it later. What Giuseppe would say, if he were here, and I'll say is, because we cannot state the uses, we cannot take the uses of the screwdriver and other things, that the uses are indefinite in number and unorderable, and some of them may be grafted into cells selected at the level of the whole. We cannot say what the relevant features are by which the phase space changes. So it's not the same as the expanding lattice. And Max, you can try it with the n plus 1 dimensional particles in a box. Now, point 25 I get from Giuseppe. If he were here, he would give you a long discussion about the syntactic approach to mathematics and why it isn't sufficient, and Gödel's theorem, and so on. There's a constructivist approach to mathematics. So this is Giuseppe, who's done the foundations of mathematics for years, in point 26. And what Giuseppe claims is that to do mathematics, what you have to have is you have to have semantically laden concepts. And they have to have settled meanings. So, for example, he says, if you think of the law of the pendulum, you need to know roughly what a mass is and a length is, and then you can do the law of the pendulum. Or, if you take force is equal to mass times acceleration, we kind of knew what mass was. two equal-sized rocks that kind of heft the same, have sort of the same mass, and they accelerate less rapidly than if there's only one of them if you push it. Okay, so you get F is equal to ma. But that leads then to the following. We do not have settled this is point 26. We do not have settled semantically laden concepts for the evolving biosphere, for the newly relevant degrees of freedom. And we can't restate them. Therefore, we cannot write down equations of motion for the evolving biosphere. We can't write down equations of motion for it. We don't have equations of motion for the evolving biosphere. Same thing for the economy. Try to write down equations of motions that will get you from the ENIAC to Facebook. Okay, something feels wacky about it, right? Okay, so we can't do it for the biosphere, and we don't have to depend upon human cognition. So the phase space is changing, and it's changing in ways we can't say, so we can't mathematize it. Now, if this is right, it means not Wigner's famous line, the unreasonable usefulness of mathematics in physics. And it's been unreasonably useful. It's been fantastic. In biology, there's a reason Darwin doesn't have any equations in the origins of species. And this is it. That's why he doesn't have any equations. He can't write them down. I want to make a big point here. They're synchronic and diachronic. Do I think there's a reductive account, or an emergent reductive account of my heart? Sure. Okay, and docs do a good job, and you get things like atrial fibrillation, the spiral waves, and all that stuff. Do I think that there is an entailing set of laws for the evolution of life? No. So I'm drawing a distinction between diachronic and synchronic. Okay, I think that there's an account of you now. I don't think there's an account of your becoming over evolutionary history that's an entailing one. Thus, 28. Oh, there's another point that I'll make two ways.
Where do people like Hamilton fit in this model?
I don't think it helps, but let's come back. Okay. You have to have. I think Hamilton needs a phase space. You don't have a phase space that you know.
Well, you kind of do with the population and kinship.
Oh, that Hamilton.
Yes. Sorry, I meant the
no,
Hamilton,
sorry.
Not the quaternion one.
Let me finish and let's not quaternion Hamilton, kinship Hamilton.
Yeah.
Okay. If you want to try to write down a dynamics for the coming into existence of Darwinian preadaptations, Hamilton's not going to help you. Okay. Okay. There's another point to be made. Again, that Liz and I realized when we were having tea. Without a predefined phase space, we do not know the adjacent possible, I'm on point 27, we do not know the adjacent possible niche, which is a boundary condition on selection. For example, the worm evolving to live in the swim bladder. So even if we had, which we don't, the laws of motion for the evolving biosphere, and we don't have them, even if we did have them, we don't have the boundary conditions. So we couldn't integrate the equations. It'd be like trying to integrate the equations for the motions of billiard balls on a table whose shape's changing all the time in ways you don't know. You wouldn't have a mathematical model, right? You wouldn't have a complete mathematical model. You can't do it. Now, I'm going to give you in point 29 another slightly subtler view of this issue of no boundary conditions. Brian Beckage is a friend of mine up at the University of Vermont. He's an ecologist. And Brian was saying to me about 2 or 3 weeks ago, you know, we ecologists don't really know what a niche is. And I said, yeah, I'm a developmental biologist, but I don't know what a niche is either. Then I said, Brian, why don't we try the idea of task closure and see if that'll help us figure out what a niche is? And he said, that sounds like a neat idea. And then I realized something funny. The niche of an organism is its abiotic and biotic environment. And in that abiotic and biotic environment, the organism, call it a cell right now to keep it simple, achieves task closure. Right? Now here's a funny example. Can you wash the dishes after dinner if there's no dirty dishes? No. You gotta have some dirty dishes to achieve the task of washing the dishes, right? This means the following, that given a Darwinian preadaptation, you cannot define the task closure of the organism independently of defining how the tasks are closed in its niche. The niche and the task closure are circularly defined. I'll give you another example. This is at a level that I can understand. I just made this company to make mops, and I can understand mops. Okay, so I'm trying to sell mops, and nobody's buying my mops. So I paint my mops orange, the handles. Nobody buys. Then green. Nobody buys them. Finally, I paint them striped, orange, red, green, yellow, and blue, and I carry the stripes out into dye out into the mops. Everybody's buying my mops. If you've ever started a business, that's what it's like. Okay, you rummage around trying to figure out what the heck the market is for a product you can make. I know, I've started 4 companies. Okay, you never follow your business plan. What did you just do? You found the market niche that defines your activity. Your activity is to make striped mops and make a living selling striped mops into a market. You can't define the niche and you can't define your task closure independently of one another. That makes my point. But since you don't know the niche ahead of time, you can't use it as a boundary condition. It's another way of saying the same thing. So you can't integrate the equations. So I'm on 30. I'm almost done. Well, we are beyond Newton, Einstein, and Schrodinger, and even Darwin. Why even Darwin? Darwin was amazing. Darwin did not see radical emergence. He didn't see the point that no selection is involved in creating the adjacent possible niche that picks a new direction for the becoming of the biosphere. Darwin didn't see that the biosphere is building or enabling its own future directions of becoming. To use an American expression, the fact that the biosphere is building its own or enabling its own directions of becoming blows me away. And I have to say I find it enchanting. It's enchanting. Somehow it's utterly empowering. Because the same thing's true in our economy and in our lives. We think we live, since Newton and Aristotle, in a nexus of causes, and we do. Equally importantly, the biosphere and we live in a nexus of enablements and ever new niches. And we create the niches that enable, okay? Which raises utterly new questions. How is it that when we enable something, it enables the next thing that enables the next thing that enables the next thing? This is MIT. You guys are doing technology. You're doing this all the time. Look at the last 150 years. Everything that you've done enables something else. And to make a concrete case that I brought up in class, how do you know that what you enable will be used for the reason that you thought it would be used for? And I make a dramatic case. On 9/11, perfectly fine airplanes were used as flying bombs. They weren't designed to be flying bombs. They worked too well, okay? So I think that in fact, we really are someplace new, utterly new. I do not think we can do Newton, Einstein, Schrodinger. I do not think we can write down entailing differential equations with initial and boundary conditions, integrate, and entail the becoming of the biosphere. Therefore, the world does, in fact, by this radical emergence, as Heraclitus said, bubble forth. It does. It bubbles forth beyond entailing law. It's the end of a physics worldview, Heraclitus in the watershed of life, bubbling forth radical emergence. So our lives are new. We are empowered by unfolding webs of niche creation, enablement, and radical emergence, not merely entwined in the web of causal laws. We may become re-enchanted, the biggest issue, and with it, the other biggest issue. We may figure out what it means to move beyond modernity. Thank you. I'm so glad to have had a chance to give this talk here. Thank you.
So do you want to take the questions, or do you want me to help field them?
I'll take them.
Just the pointed people.
You need to lie down.
Or you're going to point at people, you're comfortable.
Sure, I can point. I can point at people. I'm 72 years old. Yes.
Sure. So, do you think that, so moving from one, moving from the smallest piece of time to the next piece of time,
You mean
there's
Planck timescale?
Right. Are we missing a piece of physics to move from one point to the next point? Because if it's really the case that we can't write down a set of differential equations to describe where it's going, that means that at some scale we're not able to say what happens between A and B.
I hear what you're asking. Let me try to say it. Is the problem you're asking that there's some finite grain to time, and thank you, Newton, but you gave us this differential equations in continuous time or something like that. But let me try to answer you. I think a sufficient condition for my argument is Kant's notion of a Kantian whole, and Darwin's argument, and preadaptations. Okay, it's because the Kantian whole is selected, given all that I said, that reveals the newly relevant variables, namely the uses that are unorderable and indefinite in number but find a use. Given that constellation, there's a new thing in the universe, a Kantian whole. And I think my story holds in the case of Kantian wholes. So I won't to say that Kantian wholes are a sufficient condition for the argument I'm making, and therefore the watershed of life. Okay? Now, let me back off. I don't know that they're a necessary condition. I mean, this whole thing is only, well, it's been going for 10 years, but it's coming to a culmination of Giuseppe now. Gabor Vate, who's in this room, and he and I are colleagues working on quantum classical fun stuff. Gabor is trying to think about Kantian wholes in the abiotic universe, and I want to join him on that. I mean, for example, is a galaxy a Kantian whole? It kind of feels like it might be one, but doesn't look like it evolved very much. So I don't know if, so my answer to you is that there's something funny about Kantian wholes that makes this argument drive through. And therefore it doesn't seem to me that it's a problem of a graininess of time, which doesn't mean that a graininess of time isn't another problem. But I should go on, okay? Yes, you next, Brian.
Yeah, obviously what's very key in your discussion is the notion of causation. You want to speak about Darwinian preadaptations as being acausal in some sense.
Because quantum,
Uh-huh.
on Copenhagen.
Okay. I'm wondering, however, you mentioned briefly Aristotle and Newton, and you sort of put them on the same level.
Hang on, can I say something back to that? I'm not sure that the acausal part is so critical. I think the Kantian whole part is critical.
Okay.
Okay.
So
Anyway,
you
go back.
mentioned at some point that you sort of put Newton and Aristotle on the same level as saying, well, we're out of that causal universe. But of course they have very different concepts of causation,
Sure.
the two of them, and the main part is that Newton throws away the idea of final causation. Might there be some way of retooling Aristotelian final causation and finding some use of it?
Thank you so much for asking. And thank you for picking up final causation. Because my guts go the same place yours just did, Okay? Suppose that we say, contrary to all of our scientific training, that honest to gosh, we have free will. Okay? I've written an article that is in press in the Alan Turing Centennial volume. I'll advertise it here. It's called my article is called Answering Descartes Beyond Turing. See, again, at 72, you get to have radical titles. I think I've got the beginnings of an argument that involves some quantum mechanics. I borrowed from Penrose, but it's quite different than Penrose.
Henry Stepp.
And Henry Stepp. I borrowed from both of them, but it's still quite different from them. And it's online, ECAL 11, ECAL 11. And Chris's class has it. So it's here on campus. I've hit you with the two big things I've done in the last several years, wanting to impale it into the middle of the heart of American technological mastery. Okay. Anyway, you asked whether or not we could do something with Aristotle. Final cause. Let me come back to a point about Newton. Bob Rosen did an elegant book called Life Itself, in which I think he rightly argues that what Newton did is mathematize efficient cause as differential equations and integration. It's a beautiful analysis. Okay? The problem with Bob's book, we were old friends, is that the category theory that Bob has requires that you can pre-state the categories. And just the point about the evolving state space is that you cannot pre-state the categories. And I thought he was wonderful, but unfortunately he died. So let's come back to your point. If we admit free will, then I think we're home free. Because let's take Steve Jobs, recently deceased. An amazing man, we all agree. He did what? He envisioned, given the widespread sale of the mainframe computer, what did Jobs do? He said, you know what? We could make a computer on everybody's desk that changed their lives, that they could live with, and he envisioned a niche, right? He envisioned an opportunity, and he seized it. Now, if he's got free will, that's what he did. And that's consistent with what I've written in this article, which links quantum stuff and classical stuff. And if you want to read it, go read it. Okay. I'm more confident of what I said here today than of that. Okay, although I'm in love with that paper as the best try that I can make. So, but now let's come back to the parallel in biological evolution, where I will use the quantum mechanics part. Here's the swim bladder, and a quantum on Copenhagen, acausal, indeterminate event happens, such that a mutation happens, and a slightly fitter worm is now living in the swim bladder. So we cannot say that the swim bladder caused the emergence of a worm that lives in the swim bladder. Okay? It enabled it. Enablement is a powerful new idea. Okay? So in the abiotic world, we don't need free will. Once we've got free will, we've got precisely Aristotle's final cause. You need responsible free will to have Aristotle's final cause, the purpose for which the house came into existence because I wanted to build it, right? So it closes the loop. And I think that they may be tied together, namely, to just say a word about this paper of mine that I'm not going to talk about. If you hold the classical physics, you will never break the Cartesian problem that res cogitan can't act on res extension, because if you've got the mind and the brain is a classical physical system. Under causal closure, its current state is sufficient for its next state, so there's nothing for mind to do, and there's no way for it to do it. Should it make the billiard ball swerve on the table? You'll never break it if you stick with classical physics. So given what we know, the only move is to try to do something with quantum mechanics, and I think Penrose is right. No, I think Penrose found a pathway that might work. We don't know that he's right. Yes?
My question is follow. You talk about the example of the swim bladder. There's a wonderful, the essay by Ing and by Dawkins on the evolution of the eye is comparably interesting. At what point do you declare something a swim bladder? At what point do you declare something an eye? Because I think that's sort of essential to your argument both on the Kantian whole and on the components that go into it.
Well, that's a really neat question. Would you by default, look, I've never thought about your question before. So here I am and I get a little red spot. I've read Dawkins too. You get a little red spot and it's light sensitive. And it's just great because I can kind of swim towards light and maybe there's something good to you over there, something like that. If at every stage, Dawkins would argue, if at every stage I've achieved an improvement such that by a circular definition of me and my niche, circularly defined, you can't define me and my niche separately. No, you can't define my task closure and the niche in which I achieve the task closure independently of one another. If at every stage in that, I'm better than my mutant variants,
I'm sorry.
I win.
Yeah, but unfortunately, the existence of that red dot, almost by, as you yourself point out, creates that unanticipated adjacency because I can now, quote,
Yep.
see.
Yeah,
So who you are has now has changed as a function of that capability.
absolutely. So so you're making a point that's totally consistent with what I'm saying.
Okay.
All of a sudden, for goodness sakes, seeing came into the universe. The phase space of biology just changed in a way that nobody could have said.
Right.
Right? Right. But you raise another question. When do you
But do I
declare
call
it?
that yeah.
When do you
Yes.
declare it?
Right.
Well, we'd both say the same thing. You can see a little bit, right? And you're fitter than those that are unlucky enough not to have the red spot. So you know, if you do in fact beat them out, okay, because you could get a rock could fall on you after all, okay, or it could get dark, okay, could fall into a dark cave,
Right.
okay. Then evolution goes that way. Among the things I've told you, what I find most enthralling is the idea that the biosphere is building without selection its own future possibilities of becoming. That's so far from Newton. Yes?
I actually have two questions. First is, when you said that if we count all the possible atoms and all the possible combinations we can have for protein, then we'll have way many more proteins than what we have. So underneath what you just said, does that indicate if we think of the phase space of the proteins, it's actually much smaller than the phase space of all the possible molecules that could possibly exist?
You mean proteins or?
I just mean, I was trying to make, when we say a phase space of life, it's the life we know it or life we could possibly know it, but that phase space is still much smaller than the phase space of what all could possibly happen.
Sure.
So in that sense, although the phase space is moving all the time, it's moving within this much larger phase space of what could be possible. And then the second...
No,
right.
but Hank, can I respond to that?
Yes.
See, I don't think you can say what you're trying to say. I mean, of course you can say it, you just said it. But let me tell you why I think you really mustn't. When you talk about proteins, you know what you mean. You mean a sequence of amino acids, right? Okay, strung together. So you know what these things are. They're some linear string of amino acids linked by peptide bonds. But what about the possible uses of proteins? Okay, That is to say, just like the screwdriver, maybe a possible use of a protein is that it's a proton pump, or maybe it absorbs a photon and you know, turns purple and spits out jujubes, right? That is to say, I guess I want to say two things. The space of uses seems to be indefinite, one, and two, why are you stopping at proteins? Why not go to all organic molecules, and then why not go to all of the pebbles out in space? And then you know, why not go to space chemistry? I want to say something about that in a minute. There seems to be an indefinite hierarchy upward in complexity. Skyscrapers are pretty big, and they exist in the universe too, right? So I don't know how to think about this. There's this funny openness in uses by which things that are of use come to make this another thing, which is, I could only partially say this. Suppose that what Giuseppe and I are trying to say is right. Well, what does it mean about science? Well, first of all, we can still do paleontology, and we can do history, and a lot of other. I think we can do statistical laws. For example, I don't think we can predict the detailed evolution of technology, but I think we can look at sort of the branching patterns of technology, kind of like genealogical trees. Max is sitting here, and I are both playing with ensembles, and we can look at how ensembles vary over time. And there's something else that I feel that I can say it, but I don't quite know what I mean. If I have an autocatalytic set and another autocatalytic set, can the peptide in the first set help a peptide in the second set catalyze a reaction, and vice versa? Sure. So can Kantian wholes be mutualists? Sure. Can they eat one another? Sure. Can they make worlds with one another? Sure. Maybe we can begin to build a theory about how Kantian wholes make worlds with one another. And this is happening at the level of organisms in the biosphere, and it's happening at the level of corporations making worlds with one another in the economy. It's just that we don't think about enablement and making worlds and all of these things yet. We don't have this framework of question. Brian.
Yeah. Well, we have a limited time. I think there's a complication in your approach to the point where you say we don't know a set of possibilities, but mathematicians can do this. They just say the set of all possible combinations and so on, and there they point to it. But so
they point to it exactly.
but I think where you're right, and I've made similar arguments, is that if you want to be specific, then you're limited in what you can say. So I think there's overlap with our approach in that you, the universe of things you can treat by a certain approach is limited, and to deal with biology we have to go beyond it. We can't actually state the state of an organism in such a way as to be able to predict how it's going to behave, because we can't get the knowledge necessary in indefiniteness even in classical biology. Matt just mentioned that there are various people are going in similar directions. If people search for shifting assumptions in science, they'll see a video based on a symposium set up by a Japanese businessman in 2008, where
Really?
there are lots of perspectives on limitations of science. And also developing an approach of my own, which is in the physics preprint archive.
Is this the paper that you sent me?
It's the one I mentioned, yes.
Yes, I read
This is
it.
Brian Josephson, for those of you who don't recognize him from the back. And if you want, he's just posted a paper on the archive.
Yes, I posted too because I wanted to see if they would automatically move a paper of mine to general physics, but so you'll see too that my chap didn't work. He did allow it to appear in quantum physics. Because one of the two appeared recently.
How are we doing on time?
We're just down to about a couple of minutes, so we're down to the last question.
Yes.
I'm interested in systems engineering, in particular complex systems.
Yes.
What are the implications of this theory. I don't know a lot from peptides. I get glazed over when I talk about peptides. But from a systems engineering point of view,
I actually have an answer to that question.
do we wait for the adjacent possibilities to reveal themselves? Do we envision a speed field? What might be the tool, the fundamental tool?
So let me have a try, then you answer it.
Please.
I'm so thrilled I have the chance to be here talking to you. So let's talk about this adjacent possible.
You only have 2 minutes.
I think the adjacent. I think there's something true about the adjacent possible. For example, when Steve Jobs thought up his idea, do you think he could have gone to a venture capitalist and said, "I've got this great idea, personal computer, Apple's a great name, logo, the little thing cut out. Would you give me 20 million, please, for 90% of my company, or $1 million for 10% of my company, whatever?" Well, the VC would have considered it, right? And so they'd have gone through a discussion about the risks, the market, and all that stuff. What's the status of the possibility that Steve Jobs, what's the ontological status of the possibility that Steve Jobs was bringing to the VC? Okay, question one, to leave hanging in the air. Maybe it's ontologically real. Second thing is, whatever the ontological status of the adjacent possible is, it seems that the adjacent possible is growing. And I'm going to point it out in something we all know that the economists who may be in the room won't talk about. 50,000 years ago, the diversity of goods and services in the economy was, what, 1,000 or 2? It's 10 billion in New York. There's been an explosion of goods and services, right? Advancing into the adjacent possible, just like Steve Jobs did. We don't have a theory of it. Actually, I do have a theory of it. It's sitting in my book, At Home in the Universe, but it's an algorithmic theory, which is better than nothing. I don't think the real process is algorithmic at all. I think it keeps solving the frame problem, which computers can't solve. So I want to ask a new question. If there's an adjacent possible, how is it changing over time? It looks like it's getting bigger. That is to say, it's easier to invent something now than it was 50,000 years ago. How come? It's true. How come? And it may be so we need a theory of niche creation as a function of the number of things that are around making their worlds with one another. And my bet is that the adjacent possible is growing. And a dream of mine, and it's a dream, is that the biosphere is growing as its adjacent possible, as a secular trend, as fast as it can. And it ties into engineering because whether you like it or not, you are enabling ever new adjacent possibles. Whether they're airplanes flying into buildings, okay, or people meeting needs, or using your artifacts for things that you never would have thought. We must begin to think what wise enablement is, and how we will do it, and how we will adapt to correct our mistakes.
And
now you answer.
That's a fabulous answer. I don't think I need to add anything to it. And let's thank Stu.